Oh, like you got like 5 minutes. Weekend.
It was good.
Good.
Yeah, I actually hosted a bunch of my high school buddies on Friday last week.
Oh, nice.
Yeah, so it's kind of a sequel to my friend's wedding because it was kind of a reunion, and so we thought we'd invite a bunch of people over. So,
Nice.
yeah, it was cool.
Were they all people that were at the wedding?
Half of them were. That's kind of why we had to get together. We had the half that weren't at the wedding. So
Was your buddy at the wedding? Was he there?
oh yeah, he was there.
Oh, that quick after the wedding.
I know, right?
Nice.
Yeah. Yeah, but it was really nice. Yeah, some people I haven't seen in literally 15 years. And so yeah.
My dad was at one of those where high school buddies that he hadn't seen in.
Oh wow.
He hadn't seen any of them. It's like his group of friends. And I've reached out to everyone and they just did a Vegas trip.
That's awesome. Wow, Vegas. That's awesome.
He's like, I haven't brought that trip since kid.
That's awesome. That's awesome. That's cool. They can still have fun with his friends like that.
Yeah. You guys played again, or you guys hung out?
We just hung out. I mean, we had like a potluck, and so everyone brought food. So we just had a ton of food. Yeah, we just hung out and talked, drank a bit. So it was fun.
All right.
Oh, that's interesting. I've never ran into the issue. So only when you put 2 digits for the for the post diameter. Usually the answer should figure out a lot of the sig figs like that. What was the original post diameter? I think maybe if you make it too small or too big, then it's going to increase the stress quite a bit. So I think you have to be careful with that. And so if you only make kind of a small change to it, like maybe change the diameter maybe like 10% of what it was before, then that's going to be probably going to be a lot more stable from that. I see. Yeah, I mean, just do the best. Just do the best that you can. If you want to bring it in on Thursday, I'm sorry, just a quick look, see if you're here. If you want to bring it on Thursday and so I can take a look, then I can see. It's a little bit hard to kind of look on Zoom, but yeah, just kind of do the best that you can. I think that part is pretty independent from the rest of it. So okay, yeah, and so you can go ahead and try the rest of the activity, because I think the rest of the problems don't depend on that, and then I can take a look on Thursday. Yeah.
Watch House of Dragons.
No, I don't. I haven't watched any Game of Thrones actually.
Really?
I feel like for a while it was the very hip thing to do, but I don't do it out of spite. I just not that interested.
Oh, yeah, absolutely. Okay. My little sister, she's pretty young when Breaking Bad was first coming out, and she just recently. She's the type of person where she won't watch something just because how popular it is.
I see.
And she even told me, I was like, how do you like it so far? And she's like, I really wanted to say I hated it. It's so amazing. Yes.
So it converted her. Oh yeah. There's so many streaming services. That's the thing. There's so many streaming services now. It's hard to keep track of it.
Each person pays for whatever.
Nice. That's how you do it. All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Good, doing good. Midterms this week, so I'm sure everyone's really busy. I know I have midterms in a couple of my classes. Okay. But for this class, we don't have a midterm exam coming up. We do have a midterm exam eventually, but it's not going to be until Thanksgiving. And so, what you got to be working on for the next month is actually the midterm project. And so, just like I promised last week, I've modified the specs a little bit for this year, and we're going to talk about it today. Okay. All right. And so, besides that, so I think probably spend about a good 25 minutes talking about this. And then after this, we'll go ahead and pick up where we left off last Tuesday, talking about plasticity and hypervasticity. And then after that, we'll probably get into some 2D elements as well. Okay. All right. And so, quite a busy day today. And so quite a lot to cover. And so, but I don't think there's any major announcements I can make besides, make sure you're working on activity 3. Okay. And so are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and start talking about the project. Okay, and so so far, in this class, we've mostly been working on ANSYS stuff, and so we've done 3 ANSYS activities, and even a lot of the lectures that we've been having, I've kind of geared them with the idea to kind of give you background and give you perspective of why we're clicking certain buttons in ANSYS, right? And so why we're making meshing, why we're doing meshing a certain way, why we're doing boundary conditions a certain way. What do material properties mean and all that, okay? And so the midterm project is kind of your chance to kind of put it all together, okay? And so basically, the way that you can think of the midterm project is that your midterm project is what I consider to be, a fairly professional, finite element, analysis and study, and as well as the report, okay? So this is kind of very typical of what you would do or how you would conduct a finite element analysis in practice, right? And so you get your geometry, you would run the simulation, right? You would justify all your decisions. And so, all the decisions you would make in terms of meshing, in terms of boundary conditions, in terms of material properties, right? And so like we've talked about over the last few weeks, you have to choose all those things very thoughtfully. And so you can't just do them at random, okay? And then you're going to write a report on it to not only detail your results, but also to convince people that the way you set up your FEA was legit and the result that you get can be trusted. Okay. And so that's kind of my idea, because at this point in the semester, we've covered basically all the basics of ANSYS, and so now is the time for you to kind of put it together and and show me what you've learned. All right, and so. For this project, I am kind of constraining it a little bit more. And so, for your final project, you'll be able to choose, any subject that you want. But because of this is a midterm project, I kind of want to constrain it a bit. Okay. And so what you'll see on Canvas, and so if you go to the assignment page in Canvas, some of you may have seen this already. I've posted the CAD files for 3 different geometries, okay? And so you can see some screenshots of the different geometries here on the project specs. And so on the one hand, the first geometry here is a bearing housing, okay? The next is this kind of turbine / airplane blade, okay? And finally, we have a wall bracket. Okay? And so for this project, what you're going to have to do is you're going to have to just choose one of the geometries. So don't do all 3 of them. So just choose one, and that's going to be the subject of your study of your project. Okay. And so I'm giving you a month to do this, and so definitely choose carefully, because once you kind of choose one, and once you start running some simulations, it's a little bit hard to kind of switch, because you kind of have to start everything over. So think pretty carefully about which one you're going to pick. Okay. And so there's no, I'd say they're all equally difficult. And so they're not, one's not easier than the other ones. And so, and you're not going to get extra points for doing one or the other. And so it's really just up to your preference about, what you want to do and what you can imagine yourself doing for the next month. Okay. Okay. All right. And so that's the first part of the project. And so the first part, you're going to choose which geometry that you're going to do. And then you're going to start working on the, simulations. Okay. And so the way I'm going to describe this is that, I have this section here called project requirements. And so what I'm going to do is I'm going to go through each of the sections here and talk about, what you should be thinking about in each section and what I'm going to be expecting from you from this project. Okay. Okay. First is going to be the project objective. Okay. And so this is something, we haven't really talked about in the class yet. Okay. So this is, I think, probably the newest part of the project. But it's nothing that you haven't seen before. Okay. And so basically the idea with your objective is that, you should have a purpose. You should have, a good reason for running your finite element simulation. Okay. And so a lot of times, especially once you're in industry, to run a finite element simulation is a decent chunk of investment. And so it's an investment in, first of all, time, right? And so it's going to take you time to set up the simulation, to develop the CAD files and develop the simulation files. But there's also an investment in, in the power it takes to run the simulation. There's investment in time for other people to look at your simulation results. And so, even though a simulation we say is relatively free, and that we don't have to run an experiment, there's still some time that's required for it. And so you want to make sure that you're running a simulation for a good reason, and to produce pretty pictures is not a good reason to run a finite element simulation. Okay. And so the first thing I want you to think about, after you've chosen your geometry, is I want you to think about, what could be a good reason for you to run a simulation on this geometry. Okay. And so in this second paragraph here, I have some questions that you can consider, to kind of help you out with, with determining an objective. Okay. And so for instance, maybe you're interested in the mechanical stress in a critical part of the geometry, right? And so if you look at, let's say the bearing housing, right? Right. And so from this geometry here, you can see it's probably going to house a shaft that's going to go in the middle, right? And so, what are some stresses that can occur on this bearing housing and how can it fail, right? So maybe your objective in your finite element analysis is determining, based on certain loading conditions, where is it most likely to fail, okay? Right, and so maybe that might be your second question, right? And so another question is, maybe you're interested in seeing, if the part will fail under typical loading scenarios, okay? Or maybe, you might be interested in what's the maximum deflection, right? So maybe you're interested in the deformation, and that has some significance to your, to your part as well, okay? Or maybe, maybe what you're looking for is maybe you're looking to minimize the cost of production, okay? So maybe you're looking to choose the best material that satisfies your specs, but still satisfies all your design requirements, okay? Or maybe you're using finite elements to design or to better design this part, so I want you to be creative here. So this is kind of where you have to use your imagination a little bit and kind of think about, where will this part be used in practice, and, what would someone be wanting to find out about this part from an FEA that they wouldn't be able to find out normally, okay? And so really give this objective some thought, because, I'm going to grade you on the objective quite a bit on this. Yeah.
Are we to set like goals for our objective? Like, oh, I want it to meet, like I need it to be under this level of stress.
Yep.
So we're actually setting those.
You are setting those goals, yes.
Okay.
And so
it doesn't really matter at the end of the day if it makes that goal or not, right? we're just seeing if it does.
Right, and so the goals here are basically going to be there to drive your analysis, and so whether they meet the goals or not, I mean, this is a made up part, and so you're not actually be fabricating this, but you want something to drive your analysis, and so you want to first of all, it's going to drive what kind of loads you're going to put onto it, and so kind of the objective that you have and the goals that you have, it's going to drive what kind of loads you put onto it, what direction they're going to go, what magnitudes they're going to be, and so I want you to think of that first because that's going to kind of drive everything else.
Are materials already set for these different things?
They're not, and so I'm going to let you choose which materials that you want as well. And that's going to be part of it too. And so I want you guys to think about what are some typical situations that these parts are going to be in, and what are some reasonable materials, or what are some typical materials that they're going to have, and then input those properties in yourself into ANSYS as well. We'll get to that in a bit too. Okay. Yeah, but the first part is the objective, and so that's going to be important. And so for your final project, this is going to be a big part of your final project as well. But I think for your final project, the objective will be a bit more clear because for a lot of you, I think you guys are going to you're going to do your senior design project in here. And so your senior design product, your senior design project, you already have, the goals and you already have the specifications for them. And so you just have to kind of translate that to FEA. And so for this one, I'm giving you the part, so you kind of have to use your imagination a little bit. But having that objective first is really important as you start to do the other parts of the FEA. Yeah.
This is a solo one though, right?
There's solo,
Final.
yes.
Okay. But the final one's a group.
So the final project, I've designed it to be solo, but I know because several people here are from the same project, and so I'm willing to entertain some groups. But we'll talk about that kind of once we get there. Yeah. But for the midterm project, this is completely individual. So there's no groups for the midterm project. All right. Any other questions on the project objective? Okay. All right. And so once you have your objective down, then that's kind of when you start to sit down and start to kind of set up your FEA. Okay. So remember, we've talked about three kind of main components of the FEA. So you have your meshing, you have your boundary conditions, and you have your material properties. Okay. And so you're gonna need to make decisions on all three of those along the way. And so I'm not going to be telling you anything about those. And so you're going to have to choose what's the best mesh to have, what's the how are you going to load it, how you're going to constrain it, and what materials you choose. Okay, so I'm leaving that all to you. And so for this part, I'm not necessarily grading you for the actual values you choose for those things. And so I'm not looking for like a certain number of elements in the mesh. I'm not looking for the mesh to be a certain element size or anything like that. What I'm more interested in is if you can make those decisions on your own, and if you can justify them, based on what we've learned in the class, right? And so what I'm looking for more is, I'm not looking to say that, you have a certain load of X amount here, right? And so, that depends on your objective, right? What I'm more interested in is that, you can say that I chose to have a load of, let's say 500 pounds here. And the reason for that is that this 500 pounds represents this, which relates back to my objective. No problem.
So these three different scenarios, each one's going to be done individual of the other, right?
Exactly. Yeah.
We'll combine three.
Exactly. Yeah. So we'll get there. We'll get there in a second. Yeah. Yeah. But yeah. So for this one, I don't care as much, how much you met. Although if you come to me with like a 15 element mesh, of course I'm going to ding you for that because that's going to be a really bad mesh. But as long as your mesh is reasonable and you have a good justification for it, in terms of how you chose the element size, how you chose the element order, things like that, then that's what I'm more interested in. Okay, because what you'll see is that when you get out and you do FEA professionally out there in the real world, people are going to challenge you on kind of every decision that you make. So they're going to ask you, how many elements do you have? Why did you choose that? Why did you choose the boundary conditions this way? Why did you choose this material properties? And so you have to be prepared to answer these questions. And so this is kind of your first real test on if you can kind of justify all those decisions. Okay. Okay. And so relating back to the question that was asked, the strict requirement that I have is that you run basically three different simulations, or what I call three different scenarios for your part. Okay. And so I don't want you to just do a single simulation or a single loading scenario. I want you to do three different ones, all according to your objective. Okay. And so each of these three different scenarios, they're going to be three separate simulations, and each of the three have to be different in some way. Okay. And by different, what I mean is that the boundary conditions have to be different, and or the material properties have to be different. Okay. But with that said, among your three situations, I want at least two boundary condition setups. Okay. And so, don't just, run the same simulation with three different materials. I think that's a little bit too easy. And so I want you to change up the boundary conditions at least once among those three scenarios. Okay. And so I have an example here, to kind of show you what three different scenarios would look like. Okay. And so let's say that you're running a simulation on a part and you're choosing structural steels and material properties. You have a single fixed support and single tensile load on the part. Okay. Another scenario where you would change up the boundary conditions is, let's say that you have the same material properties, and so the same structural steel, you have the same fixed support, but instead of a single tensile load, maybe instead you have two compressive loads. Okay, so that counts as a different scenario. And then a third scenario would be, maybe use the same boundary condition setup as either one or two, but then you change the material properties to plastic. Okay, and so that would constitute as kind of a third scenario. Okay, and so here, you have to, and so you're going to have to use your imagination a little bit here as well. And so, think about, how your part is typically used in practice, and what are some reasonable loads and constraints that you can put on, as well as some reasonable materials that you can use. Okay, and again, it all kind of relates back to your objective here. Okay, and so what I like to tell people is, what I like to do is, kind of do a little bit of storytelling, right? And so think of a story of how your part's being used in practice, and then use that story to kind of guide you in how you choose, the loads, constraints, as well as the material properties. Okay, right. So you have to use a bit of your imagination. Okay. Any questions on this? Okay. All right, and so that's everything with the setup. And so then, after you have the setup for all your simulations, of course, you're going to run them, and then you're going to report on your results. Okay, and so the next section is going to be your ANSYS results. And so this is going to be very similar to the activities. And so, I want you to show basically screenshots of your ANSYS results. And so at the very least, I want you to show the total deformation and the equivalent stress. Okay. And so basically for each of the three scenarios, you should have at least two screenshots. Okay, so there should be at the very least six result figures in your report. Okay, but what I want you to do additionally to that, and so I think this goes beyond the activities, is I want you to explain your results in the text. Okay, and so it's not going to be enough just to give me the screenshots of the total deformation and the equivalent stress. I want you to kind of explain to me what I should be looking at in these figures. Okay. And this is pretty typical too. And so, for the activities, it's a bit different because, I know everyone's kind of doing the same thing. And so I know exactly what I need to be looking for. But normally, when you run an FEA in practice, your reader, which is going to be like your manager or someone like that, they're not going to know what to look out for in your simulation results. And so you have to explain it in the text so that they kind of know what to look out for. Okay. And it could just be as simple as like, here is my plot of the total deformation. I see the maximum deformation is this, and it occurs in this location. Okay. And that relates back to my objective because of this. Okay. So it could just be as simple, just, maybe 2 or 3 sentences, but, that explanation in the text is really important just so people kind of know, what they're looking for. Okay? And if you need kind of justification for this, you can try, showing a screenshot of ANSYS to someone that's not inside this class, and ask them to pick out, what's the most important details, and you'll learn very quickly, why that explanation in the text is important. Okay. All right. But besides, the total deformation and the equivalent stress, feel free to include other screenshots as well as you think are relevant. Okay. They're not required, but if you think that they enhance your report and they enhance your objective, then you can feel free to do that as well. Okay. But at the very least, for each scenario that you compute, I at least want to see the total deformation field and the equivalent stress field. Okay. All right. Any questions on that? Okay. All right. And so that's the bulk of the report. And so after that, you're just gonna write some concluding remarks, and maybe answer some questions here, and then that's it. All right. So oops. And so some other materials I'm providing you. So I've posted a template for the report. And so if you go to the Canvas site, and I'll show you in just a second, I have a Word doc there that shows you basically, how I want the report to organize. Okay. And so please use the template. At the very least, use the same headers as the template. It makes grading a lot easier. And so if you don't use the same headers as the template, it just becomes a lot harder to grade. So at least use the headers. You don't have to use my font. My wife tells me all the time that I pick the ugliest fonts, and so you don't have to do that. But at least use the headers from the template, because then it just makes my grading a lot easier. Okay. People ask me all the time, how many pages I expect the report to be. Honestly, everyone's reports are going to be different length because it depends on how many screenshots you include, how you format the report. So I don't have a page requirement. And so, I have a rough range here of 12 to 15 pages, just because that's what I've seen normally in the past. But you don't have to be in that range. And so I've seen reports that are maybe only 8-9 pages that get 100%. But I've also seen reports that are like 50 pages that I've given like a D to, because it's they just put way too much fluff in there. So I'd say this is about the average, but don't look at this as a requirement. So I don't knock you off on strictly on the number of pages. Okay. I don't mind Comic Sans. My wife hates Comic Sans with a passion because she's a graphic designer, but I don't mind Comic Sans. Yeah. Yeah. Okay. And another thing I posted is a rubric, and so I'll go ahead and show you the rubric after this as well. And so you can use the rubric to kind of gauge how much points each portion is worth, and you can look at it and see what I'm looking for specifically for each section. Okay. All right, and so what I mentioned before is that this is a solo project, and so there's going to be no teams. But with that said, because you're probably going to be working on either the same part or very similar parts to to your friends, I do encourage you to work together in terms of debugging, answers issues. So if you're getting an error, you can talk to your friend about it. That's fine, but don't write your friend's report. Okay, and if you do, it's very obvious. So everyone should do their own. Everyone should write their own report, but you can work together to kind of help debug the simulations. Yeah. All right. Question: is it okay to use LaTeX to write a report? Absolutely. Yeah, I love LaTeX. So LaTeX is LaTeX will make your report very clean, and so definitely I encourage you to use that if you feel comfortable. The only thing I ask is that you still use the same headers as the template. Yeah. Okay, and so final remarks. This project is going to be a decent amount of work. Both in terms of the simulations and the writing. And so throughout this whole process, please don't hesitate to reach out. I know there's quite a lot of steps to the project. So I'm here to help you throughout whatever steps you're at. And so come to office hours, send me email. So I'm here to help as much as I can. Okay? And before I forget, due date. You might have seen it earlier, but the due date is going to be basically right before Halloween. And so the due date is going to be October 30th. And so you have a little bit over a month to do this project. Okay. Okay, so I'm going to show you the template and I'm going to show you the rubric. But besides that, are there any questions on the specs here? Yeah. I have no idea, and so I got this online, honestly. And so I picked it for this project because there's not too much going on with it, so it's a relatively simple geometry. But I'll leave that up to you in terms of what kind of turbine blade is it, and what you can imagine for it. Yeah. Yeah, so I wanted to finish it before Halloween because I know, I like to have fun on Halloween too. And so, I want to have this due before then. So, so you can enjoy that a bit. Okay. Any other questions on the specs before we talk about the template and the rubric? Okay, all right, so let's look at the template. Okay, so the template is here. Right, so this template is a Word doc, and so you can feel free to just, edit this one and have that as your report. Or you can just copy the headers and kind of do whatever you want. Okay. All right. And so the main thing I want you to take away from this template are the headers. Okay. And so here we have a header for introduction. Here we have the material properties, the meshing, and the boundary conditions. Okay. And you can see for each section here, I've wrote a little bit of text here to kind of tell you what I'm expecting for each section. Okay. So definitely read that up. Yes. Yes, please. Yeah, so you use the word methodology and material properties here. Yeah, so this template is very similar to a typical scientific report. And so typical scientific report, you have your introduction, you have your methodology section that kind of describes what you're doing and and the justification for it all, and then you have your results, okay? And then, you have your results for your first configuration, second configuration, third one, and then you have your discussion and your conclusion. References, I don't think you're going to have any references, unless you want to reference the lecture notes, feel free to do that, but you don't have to include that. And then here's just a little bit of additional instructions for how to do figures. And so my only requirement for figures is that you label all the figures. And so, if you put the label underneath, that's perfect. Okay. All right. Any questions on the template?
Theoretical math portion, correct?
Not here, no. Yeah. So here is just, it's just basically every decision you made in ANSYS, and just I want some justification for it. Yeah. All right, and so last thing we'll look at is the rubric. Okay. So here's the rubric. Okay. And so you can see why I want you to follow the sections, because I'm grading each section as part of the rubric. Okay. And so if you don't label the sections, it becomes a lot more difficult to grade you on that. And so, please include all the sections. And so here's a bit more information about what I'm looking for, as well as how much points each section is going to be worth. Okay. And so definitely, as you're kind of putting the report together, use the template and use the rubric, because that's how you kind of maximize the outcomes. All right, and so that's about it. And so you guys have about a month. Start. I know every professor says this, but start early. Don't leave it for the last minute, because kind of the sooner that you start, because I guarantee you, because this is the most hands-off I'm going to be in terms of your final project too. And so I'm not going to be walking you through any of this. And so you're going to run into hiccups. You're going to run into some issues as you set up the ANSYS, and you're going to run into some errors. And so kind of the sooner you start, the sooner you can run into those errors, the sooner you can talk to me about it, and the sooner you can get past it. And so, what tends to happen is that people kind of put this off to the end, and I get just a flurry of questions in the last week of ANSYS isn't working, I'm not getting this result, and they have questions about the report. And so, the sooner that you start, the sooner you can ask questions, and the sooner I can get back to you. As you can imagine, in that last week, I'm going to be pulled in a million different directions. And so, I may not get to your question, in the last week, until maybe it's too late. So, the sooner you start, it's you'll get your questions answered a lot sooner. And this has unlimited submission. Does that mean you can submit unlimited a number of times?
For the due date, yeah. So
Oh, yes. Yeah, technically, yes. But I do have turned on for this one. And so I think if you submit it kind of too many times, then Turnitin will flag it. So you can submit it, multiple times. Just try not to do it too much, because otherwise Turnitin is going to flag it. Yeah. All right, question. So we're going to have ANSYS activities this month until the submission date, or do we just work on the project? I do have one more ANSYS activity for next week, just because it kind of just follows naturally, just kind of what we're working on. But after that, that's going to be the last one until the project's due. Yeah. So one more ANSYS activity, and then besides that, you're just working on the project. Okay. All right. Okay. So that's the project. So let me go ahead and come back to my iPad. Okay. All right. And so that's the project. And so, hopefully, I know it's going to be a lot of work, but, I hope you guys have some fun with it too. Reading some of the scenarios that specifically the wall bracket was put in last year was very entertaining for me. So, don't be afraid to be really creative and really funny with that. Because I personally enjoy reading those things too. So, if you can come up with some funny situations and you make me laugh, then that's good. I may or may not give extra credit for the really funny ones. So just putting that out there. Maybe, if you make me laugh really well, then we'll see. It won't be that much. It'll just be like a point or two. But okay, so let's go ahead and pick up where we left off. And so, it's been a while since we had a lecture, because we had our activity last Thursday. And so this will be a continuation of what we went over last Tuesday. Okay. All right, and so what we were discussing back then was we were discussing material properties. Specifically, we left off talking about plasticity. Okay, so let's kind of jump back in for that. So just as a quick recap, plasticity is basically how we model, or basically any kind of deformation or stress strain that exceeds the linear portion of a material. Okay. And so what we talked about so far, we focused a lot on linear elasticity. Okay. And so if we draw our stress strain curve, okay, we know that for most materials, if you keep the deformation fairly small, you're going to be in what's called the linear region. Okay. And so in the linear region of the stress strain curve, what we have is the Young's modulus E. And so stress is equal to the Young's modulus multiplied by the strain. Okay. Right. And so if you don't do anything special in ANSYS, and so if you just do plain old static structural, the assumption is that you're going to be working in this linear region. Okay. So if you put more stress, then you can expect a linear amount of strain or deformation to go with it. But we know from strength of materials that eventually, if you push past this, okay, where this point right here is called the elastic limit. Eventually, you're going to reach this region here, which we call plastic deformation. Okay. Where the relationship between stress and strain is no longer linear. Okay. And so it's kind of start to kind of even out a bit like that. Okay. And so there's a couple kind of main features that we want to capture in ANSYS in plastic deformation. Okay. All right, so the first thing that we want to capture is the fact that our stress strain relationship is going to change. Okay. Okay. And so the fact that our curve is no longer be linear, we want to capture that, and I'd say that's probably the more important part, just to make sure that as you exceed past that elastic limit, that the deformations and the stresses that you compute in ANSYS are going to be accurate with respect to the plastic behavior of the material. Okay. So that's kind of the main thing that we want to capture. The other thing that we want to capture is the what's called the hardening effect. Okay. Okay. All right, and so the hardening effect has to do with the fact that after you achieve some level of plastic deformation, then the elastic limit is going to increase. Okay? Okay. And so we talked about this, kind of near the end of lecture last Tuesday, right? And so we know that, as we kind of exceed past this elastic limit, and so, let's say that we reach this point on the plastic deformation, okay? What can happen is that as you release this load, the part is going to relax down, okay? And so now this point right here, this is the new kind of resting configuration. Okay. And so from that resting configuration, the elastic limit has moved up. And so this point right here from where it kind of departed from, this is the new elastic limit. It does, yes. Yeah. And so it changes the slope on which you approach that line as well. Mm-hmm. And so these are kind of the main features that we need to specify in ANSYS. And each of these you kind of have to do a bit manually, unless you're using a built-in material like structural steel. Okay. So let's talk about how both of these are applied. So let's start with A. Okay. And so the change in the stress-strain relationship, you can kind of define this either one or two ways in ANSYS. And so the simplest way that you can do it is what's called a bilinear stress-strain curve. Okay. Okay. And so in other words, what we're saying is that once the elastic limit is reached, then our the slope of our line, the relationship between stress and strain is going to act with a different slope. Okay. So this is the simpler one, but it's also the one that's not as realistic. But even so, you can still get some decent behavior from it. Okay. All right. So under the bilinear, I should say model, okay, or bilinear curve, what you get is that you'll have your normal linear deformation up to the elastic limit. And then after that, you basically just draw another linear line right here. Okay. Okay. And so this region right here, this is the plastic deformation. So this one's the simplest to do because you don't, the only thing you really have to specify here is a new slope. So basically you specify a new Young's modulus for the plastic deformation region. Okay. All right, so that's the simplest way that you can do that. Okay, so you just basically specify another slope. It's not perfect, but a lot of times that's, in order to get at least decently close simulation results, all you need is just a different slope. And so, for the sake of kind of simplicity, this one's not bad. Another way to specify this is to use what they call a multilinear stress strain curve. So this one requires a bit more work and a bit more data, but basically the idea behind the multilinear approach is that you reconstruct the entire plastic deformation region kind of data point by data point. Okay. So if we draw kind of the plot here, okay. Once again, you have kind of the linear region. And so the linear region all kind of stays the same. Okay. The difference now is that instead of specifying a single slope, what you're going to do instead is you're going to define actually all the points right here. Okay. So as you can imagine, getting your hands on this kind of data can be difficult, unless you work for a company that does this testing. And so I'd say this option is more common for companies that kind of do their own material testing, and they're kind of inputting kind of all their experimental data into ANSYS just like that. Okay, but for kind of normal use, if you don't have access to that kind of data, this is fairly rare and not that useful, but it is there. So if you have information on stress and strain in the plastic region, then you can basically this is basically a way for you to input it manually. Okay. Any questions on this? Yeah. So hardening occurs whenever you kind of exceed when you deform a model past its elastic limit. And so anytime you have a stress strain that's kind of up here on the plastic deformation curve, and then you release that load. And so what happens is that because you kind of plastically deformed it, you kind of permanently deformed it, when you release that load, it's going to be a little bit harder than it was before. Yeah.
Did you say that?
Yeah, so typically it does increase the all the strengths and the stiffnesses and all that. Yeah, and so we'll see. And so we're going to go over how you specify those in ANSYS. And typically the way that you do that is you specify how much the limits are going to grow as you go into that plastic region. Yeah. Mm-hmm. Any other questions on this? Okay. All right, so let's talk about how we specify hardening in ANSYS. And so just like I mentioned, when we're talking about hardening, we're basically talking about increases in the elastic limits and the elastic strengths. Okay. And so there's basically two ways that you can incorporate hardening. Okay? And so first is what's called kinematic hardening. And so under kinematic hardening, you basically assume that the difference between the tensile strength and the compressive strengths are the same. Because there's always going to be a gap, right? Because you know tensile strength we consider as positive, right? Positive stresses are generally tensile stresses, whereas negative stresses, those are compressive stresses. Okay, and so what kinematic hardening assumes is that as you increase the strength in one direction, and so let's say that you go through some plastic hardening and then you increase the tensile strength. What that's going to do is that it's actually going to weaken your compressive strength because the difference between them is always going to be the same. Okay. All right. So the other way that you can incorporate hardening is called isotropic hardening. Under isotropic hardening, it assumes that the tensile and compressive yield strengths are equal in magnitude. And so isotropic hardening is quite different. And so as one of the strengths gets stronger, that means the other one's going to get stronger as well. Okay, so very different behavior between the two. And so and so which one you end up picking, of course, depends on the material that you have. And so you're going to have to do a little bit of research in terms of here's my material. Is it more prone to kinematic hardening or isotropic hardening? Okay. I will say that both of these hardening schemes are approximations, and so there's not many materials out there that follow either kinematic or isotropic hardening exactly, but some materials kind of follow one more closely than the others. And so that's something that you're gonna have to research kind of material by material. Okay. All right. Any questions on this? Yeah. Sure. Yeah. So I think it might be helpful to draw a picture. All right. And so actually, let me draw the picture a little bit differently. It's like this. All right. And so normally, and so on the x-axis, we have strain. On the y-axis, we have stress. Okay. So normally, we have, let's say we have a material with an equal tensile strength and a equal compressive strength. Okay. And so, just like we've seen in our activities, what the strength basically defines is that if it defines basically the maximum limit for the stresses, okay? And so what we've seen is that if the equivalent stress exceeds the strengths, right? And so it exceeds the tensile strength or it exceeds the compressive strength, then the part is going to break, right? And so these are limits that you don't want to exceed, okay? What kinematic hardening says is that, basically what we're starting with is basically this difference right here. And so we have a difference between the tensile strength and the compressive strength. So you just kind of subtract one from the other. Okay? As the part goes through, some plastic hardening, and so let's say that we've improved through the hardening process, we've improved the tensile strength to be up here. Okay? And so this is new plastic hardened tensile strength. Right. And so what the kinematic hardening basically says is that, because the tensile strength moved up, the compressive strength has to move up as well. Okay. Okay. Such that the difference between these is equal. Okay. But that's why I mentioned before that, when you kind of strengthen in one direction, you kind of weaken in the other, because now that compressive strength is actually weaker than it was before because it's closer to zero. Right? And so even though you've improved the tensile strength, you've made the compressive strength weaker because what we assume is that difference is the same. Exactly. You can go the other way around too. Yeah. And so if you strengthen in the compressive direction, then you weaken in the tensile direction. Okay. So it's kind of, kind of a double-edged sword. All right. Any other questions on plastic hardening? Okay. All right. And so, those are the options available to you in ANSYS. And so, for this class, we're not going to do too much with it because we're mostly going to assume linear behavior. But if you are in a situation where you have to consider plastic behavior, here are the options available to you. Okay, and so you can make use of both. Okay. And so I did want to go over one more thing in terms of material properties, just because I think it's really cool. But I'm going to go over it just really quickly, just so that I want to move on to the next thing, and that's called hyperelasticity. Do you guys go over hyperelasticity in maybe like 331 or something like that, or other courses? Not really. I see some shakings of head. Yeah, I didn't really learn about it until I was in graduate school too. So it definitely wasn't part of my strength of materials class. But it is really cool. And so it's kind of a new kind of way to do stress strain relationships that I personally actually don't know that much about it. I've used it in simulations before, but I can't claim that I have really expert knowledge of it. And so the way I'm going to explain to you is kind of my perspective as just a user, not really an expert. Okay. And so the kind of like the name implies, hyperelasticity, this is kind of a new formulation for describing deformations or describing the stress strain relationship when you have large deformations. Okay. Okay. And so that part of the formulation is actually very appealing because, kind of the traditional way to think about stress and strain is, kind of what we learned just now. And so, we have, a linear region governed by, a certain Young's modulus, and then past that, honestly, it kind of becomes the wild, wild west. And so you have plastic deformation, and every material kind of behaves a bit differently. And so the idea with hypervasticity is kind of encapsulate both kind of the small deformations and the large ones into kind of a single framework, so that you don't have to make this kind of weird transition between the two. Right? And so the way it accomplishes this is very different. And so instead of kind of a stress strain function, what we have instead is what's called the strain energy function. And so it's a very different perspective, because now you're kind of looking at deformation and you're looking at stress and strain from a conservation of energy point of view. And so we unfortunately we don't have enough time, and honestly I can't claim that I fully understand the full theory behind this too. But the general idea is that when you have a structure, when you have an object, it has a certain amount of potential energy that is conserved as the object undergoes different deformations. Okay? Okay. And so the idea is that with this strain energy function, you'll be able to select, different deformation states or different stress states that minimize this potential energy. Okay. Okay, and so, I'm not going to go through much of the theory, but kind of the upside to this is that you get very interesting stress strain relationships that would not be possible with kind of the traditional framework. All right, and so for example, one a type of stress strain relationship that you can get from this, something like this. And so you can see that this stress strain curve doesn't really follow the same rules as before. So it doesn't have it has kind of a linear region at the beginning, but the plastic deformation is very strange, right? And so it kind of dips down and then it comes back up again. And there are actually materials that behave like this. And so, as we kind of advance the field of material science, new kinds of composite materials, new kinds of, really wacky materials that people are coming up with, they're having, stress strain relationships that are looking like this. And so, you're going to need more sophisticated, more complex material models to handle that. Okay. Not only that, but a lot of, excuse me, a lot of naturally occurring materials also kind of follow this curve as well. And so, I'll say kind of my exposure to this is, I have a lot of background in modeling blood flow and modeling kind of bodily tissues inside the body, using finite elements for that. And so a lot of the muscle tissue, a lot of the soft tissue in your body, they have stress strain relationships that follow curves that like this, where you can't just use linear elasticity, plastic deformation to describe them. You need something more complex like a hyperelastic model. Okay. And so, that's kind of where the cutting edge is right now. And it's really cool that ANSYS actually gives you a way to model this, because it's, it's kind of, on the forefront right now. Okay. And so, I won't talk, much more about it, kind of more for the sake of time, but just know, but I want to make you aware that ANSYS does have this capability. And so, if you do, maybe not in this class, but, maybe for your final project, but, maybe if you use ANSYS beyond, maybe you'll start to use these materials as you start to use hyperelasticity, maybe if you're running simulations on, really interesting, composite materials out there. Okay. All right. Any questions on hyperelasticity? Okay. All right. And so that's it for material properties. So that took a little bit longer than I thought. That's okay. Okay. And so now, for the next, for the rest of this lecture, for the lecture Thursday and the lecture on Tuesday, we're going to be talking about meshing again, right? And so I told you that, we're going to be talking about meshing a lot in this class, because it's one thing that's really important. Okay? And so what I want to talk about first in terms of meshing is I want to go through the different element types in a bit more detail. Okay. And so let's start with the 2D elements. So 15 more minutes. Put that alarm away. Okay. Let's talk more about the 2D elements. And so, we've kind of talked briefly about, what the 2D elements are, but I want to talk more detail about, what it means to be a triangular element. How does that, mathematically differ from the rectangular elements? How do the quadratic and how do the linear elements how are they all set apart? Okay. And so, this is kind of the perfect opportunity to do so. Okay. Okay. But before we do that, I have to define something called the interpolation function, or or some people call it the shape functions. Right? I think I touched on this briefly, when we first introduced element order. But I want to kind of give it a more formal definition here. Okay? So what do I mean by the element interpolation function? Okay? And so every element in your finite element mesh has what's called the interpolation function, has its own interpolation function. And what it does is that it basically allows you to interpolate things, whether it be the solution or the geometry or whatever, in between the different nodes of the element. Okay? So as an example, let's say that we have our triangle here. And so the vertices of the triangle I have defined with dots. Okay, so these are what's called the nodes. right? So all the endpoints or all the vertices that you see in a finite element mesh, those are the nodes. Okay? And we know the nodes are really important in finite elements because that's where the ANSYS is going to solve for the solution first. Okay? So that's the first thing that ANSYS does. So first thing you do when you hit solve, and then it's kind of churning through the calculations. And so the first thing it does is compute what's the deformation, what's the stresses at these nodes. Okay. But a lot of times, and even if you're just looking at the deformation field, you're interested in what's the solution values in the middle of it, right? And so what if you want to know? What if you want to know what the solution looks like here in the middle of the element? Okay. And so if you want the solutions in the middle of the element, this is where the element interpolation function kicks in. Okay. And so to find the solution there, basically what we're going to be doing is a multi-dimensional interpolation from the nodes of the element that houses this. Okay. Okay. Everyone knows what interpolation means, right? Okay, so basically, you're basically finding the in-between value from all the different nodes. Okay. The only difference here is that we're doing it in multiple dimensions, whether it be 2D or 3D, and so we need a mathematical form to do that. Okay. Okay. And so, that's one function for the, or that's one purpose for the interpolation function. Okay. I would say it's actually not its most important function, but because of its name, because there's interpolation in the name, I introduced that one first. Okay. All right, but I would say the more important purpose of the interpolation function is that it sets the functional form for your solution. Okay? Okay. It sets the form for the solution to the differential equation. Okay. Because remember, and I'll remind you of this, many times because it's easy to forget, but FEA, at its core is just a way to solve differential equations on a computer. Okay. And the way FEA does it is very unique. And so instead of solving, remember, instead of solving the equation directly, the first thing that it does is that it assumes a form of the solution. Okay. Right, FEA isn't smart enough to solve a differential equation just straight up. Okay, and so it needs to know that before it starts, and so we need to tell FEA find the best linear function or find the best linear solution to this differential equation. Okay, and that's basically how it works. Okay, right, and so when you're talking about the different types of elements inside FEA, whether you're talking about the shape, whether you're talking about the order, okay? What's really important is that you kind of understand, what the underlying interpolation function looks like, because that determines a lot of its properties, that determines a lot of its accuracy and convergence qualities as well, okay? And so the shape, okay? And so it's both the shape and the order, okay? And so what you'll see is that, a linear triangle actually has, quite a different interpolation function to a linear quadrilateral, and the same thing in 3D too. And so a linear tetrahedron is going to be different than a linear hexahedron, okay? And it's through this that, you'll kind of start to understand, why is it that we prefer the rectangular elements, the quadrilaterals and the hexahedrons over the triangular ones. And the reason is because its interpolation function has much better properties than the triangular ones, okay? All right, any questions on this? Okay. All right, and so we have about 3.5 minutes left, and so I'm just going to show you the first element. But basically, what we're going to do on Thursday is we're going to go through each of the different element types, and we're going to look at what its interpolation function looks like. Okay. All right, and so the first element that we're going to look at is the linear triangle. Okay. So the linear triangle looks something like this. And so it's a simple triangle with 3 nodes on it. Okay. And so each linear triangle will have 3 nodes that we can play with. Okay. And so, based on those nodes, we know that we can consider this to have 3 degrees of freedom, three solution values associated with this triangle. Okay. Okay. Right, and so because of this, because we have 3 degrees of freedom, that means our interpolating polynomial can also have 3 degrees of freedom. Okay. There's enough teasing. Let's go ahead and write out what the interpolating polynomial looks like. Okay. And so the interpolating polynomial, I'll give it the, it doesn't really matter what the function is. And so I'll call it t of x and y. Okay. And so you'll see that we have three unknowns. Okay. So let me write it first and then I'll kind of explain. So interpolating polynomial for the linear triangle will have a constant term, C0. It's going to have a term that's linear in x, and so that's C1x, and then a term that's linear in y, C2y. Okay. And so the 3 degrees of freedom that I was referring to are the 3 C terms here. Okay. And so we can have at most 3 different terms or 3 different expressions or 3 different types of polynomials in our linear triangle interpolating function. Okay. And so, the way these polynomials kind of work is that you kind of have to build them from the bottom up. And so we start with the constant term, okay? And so we start with C0, that's nothing more than just a constant. Then we have a term that's linear in x, C1x. And then the next one is linear in y, C2y, okay? Okay. Any questions on this? Okay, all right, so that's all we got time for. And so, it's a little bit of a cliffhanger. And so I know some of this is still a little bit hand wavy, but on Thursday, we'll pick up right here where we left off. And I'll kind of explain a bit more about, the 3 degrees of freedom. And then we'll start talking about the different element types. So we have the rest of the 2D elements as well as the 3D ones as well. And you'll start to see the differences in their polynomials. Okay. All right, so thank you everyone for coming today. I know it's probably a stressful time with midterms, but hang in there, right? And so we'll pick this up on Thursday. So have a great evening, and I'll see you guys all on Thursday. Yeah. Yeah. What's up?
I was going to ask you about advice.
Oh, sure. Yeah. So if you, I have all my appointments available on the website. Yes. So if you search up like Cal State Fullerton BSME advising, and so there should be like a Google Doc. And so right click here. No. Yeah. And so if you scroll down to the bottom, click my name. And you have to sign in. So you have to sign in with your Cal State Fullerton account, and then it'll show my appointment spots. And so you just click on the one that works for you.
Okay.
Yeah.
If we have to hire before October 1st, would there be any way
I think I have some. I think I have a couple appointment spots open tomorrow, and I have a lot open on Friday. So you can book one before that.
Quick question.
Yeah.
For the activity 3, problem 4,
Yeah.
are these yield strings already assuming a safety factor, or
Oh yeah, they're already assuming safe.
okay, so we can go up to that limit?
Exactly. Yeah.
And then for question 5, when it says we can change the material, we're changing the material to change those yield strings?
Technically it would, but but you can assume that it's just in change.
Feedback for all
And
those.
so you can use the same load strength, and then you just assume that it's a different. So if you've already applied, then it's up to whenever I have free time to check them, basically. And so I'm just about. Are you Omar? Are you Omar? No. Okay. So so you apply for spring. Okay, but your graduation term is next spring.
Yeah.
Okay. So I'm just starting to work on those. So I've done about 5 of them, and so yeah. And so basically, whenever I can get to them, but I'll try to get them done before the end of the semester.
Also, didn't get the email for like academic advising.
Is your CWID even?
Yeah.
Okay, you're not up for it, and so we only contact the odd students for advice.
Oh, okay.
Yeah. But since you have an even CWID and you're graduating next semester, you'll probably be okay. Because we're going to check your TDA when we do our grad checks. So check everything's good, and if you don't have any.
Oh, okay. Thank you.
Yeah.
Thank you.
Yeah.
Okay, this is really cool.
What's up?
Yeah.
I have no idea. I have no idea.
If we're showing normal stress and grace,
You still need the equivalent stress.
Right, so the equivalent stress is kind of a combination of all three stresses. So if you want just a good sense of your overall stress, equivalent stress is great. But sometimes you also want the stress of each of the.
Yeah, I heard they show you their view, like stuff, like.
Usually the equivalent stress is the highest.
It's like packages.
Well, for this one, it's most of the stress.
Yeah,
So
it's just maybe. It's all the curve, like I asked it, I stopped it. The police officer says that's like. It's all their.
Yeah, so some.
Yeah.
Because the equivalent stress formula takes some different.
No.
So, yeah.
Can we ask you about graduation?
Yes, you should ask him about
That one might be a little higher.
I already checked that you built.
I gotta cancel my email for my appointment with,
Yep.
Yeah, I get that.
Okay, so for the
With Elizabeth.
assignment,
She's the
let's
other
do,
person, but she's for general.
the different loading scenarios. So for my second one, I applied like, so I had the normal forces that I just kept them, and I just applied another force, which is like, I was like, oh, somebody was like, had this kind of party and they tied a bunch of balloons to the sign. And so it was like lifting up the sign with a little bit of force.
Yeah.
Is that okay?
Yeah, that's great.
Okay, I just want to make sure that it wasn't like, it's not like balloons don't produce that much.
Yeah.
So it's like, it
It's
was,
okay. It's the fact that you're thinking about it, what's the record that's going.
Okay.
That's what I want you to do. That's practice for the midterm project.
okay.
No, I got it. That's great.
I think that's it. I haven't started the chair, but I'll have to do that.
Alright, so now I'm canceling
I
that
won't be
one.
here until Tuesday.
Oh, also, I mean,
Watch the Zoom or whatever.
recording, yeah.
Wait, how long ago did you just? Did you pay for graduation?
Like,
I didn't know. I didn't even know there was an.
Right after May.
What?
I'm in mild panic. I got the email this morning about the graduation.
I got a lot of emails.
Oh, I found it.
Where was it? What
What was
was
those
this?
classes 2023?
I'm wondering, and I've scheduled an appointment for next Thursday.
Okay.
So what needs to be done by the 10th?
Are you?
Oh, shit.
has to be done by the 10th. No, by the
Are you
first.
graduating this semester? or-
Just don't be. You don't have to go. This is your home.
Because I still have a registration appointment for my spring class.
Yeah.
I understand, is this another deadline that's optimal pending registration?
Yes, so I think if you apply for graduation, then it changes your status. But if you've already applied, they might have just sent that email out.
Because I still have the spring registration appointment, but I have a hold on my test.
Oh, you have a hold?
I also have a whole.
Okay.
So I have a hold, but my registration date is until, yeah, it's that same.
Okay, is your CWIT on?
What?
Your CWIT, your campus.
How do we know? How do we
It's not
know?
that hard, dude.
I don't even know my own number.
I don't, I have.
It's okay, he's your professor, you're a student, JD, you have to know this.
Okay, oh, that's really weird. Only the odd number should be on it.
Like, all-
Send me an email to the advising email, so you know the advising one.
Yes, I'm the advising.
Yeah, it's just underscore advising.
email.
I mean, I'll investigate it tomorrow, so I'm gonna email some people, because, yeah, you shouldn't be on hold because you're even and you're graduating soon, so.
I'm also.
I mean,
So I'm
we're all
I'm
even.
also on hold.
You guys are all on hold.
Yeah.
Okay.
We're all, we're probably all.
Because I just
Send me, send me an email and then I'll try and get in contact with records and registration, and I'll try to get you one. Okay. Because, yeah, you guys shouldn't be on hold, because it's only, usually it's the odds.
Well, that's what I thought was unusual, because, I mean, I made an account, advising meetings, I know we need one of those. I mean, I just had an advising meeting for major specific in April.
Yeah, that's
So-
spring, right?
Yeah.
That's last week.
Me too.
Yeah, so I just made another one for next Thursday.
Okay.
I was gonna do one
Yeah,
this
email.
Thursday.
Okay, yeah, if you guys can send me an email, just to let me know, I'll check your account to see if the hold is for advising, and if it is, I'll email, I'll get in contact with you. You guys should have.
I'll write you an email now, and I'll CC that.
Yeah.
Does that work?
Perfect.
Cool.
Okay.
Yeah,
Just remember you see what number.
okay, yeah, this is.
It's not that hard, bro.
Last Friday, I checked that I don't think they didn't put the hold from last Friday, and they were supposed to.
Are you all asking about the graduation stuff too?
Yeah, I only just found out about it.
Is your
right now.
CW already? I paid for it already, but I'm getting like a notification, or I got a notification, it's like, you just paid for it.
I don't know what this extra October 11th deadline is. Is there another registration or something?
October 1st is.
Let me ask some, let me
There's another-
contact some people, get to the bottom.
Dude, this is-
I think something's been done in the state, so.
This is for
Okay,
the second
because
pay bump for
Yeah, it
president
was
Reed.
weird because I didn't expect to get that email because I paid for it over the summer
Yeah.
and I had a meeting
I had
with
one in
Weiss just like, yeah, in April.
Yeah,
I was like, I didn't expect to get an email this soon. already.
Yeah.
So I was just like.
And I created
Wait,
another one.
who sent you guys the email? Was it?
It was from a no reply at,
It's the no reply email. That's the
It's the
classic,
bot,
the
right?
common one, yeah.
Yeah, the no reply at Fullerton, EDU.
Okay, so it came from higher than our
you
department.
wanna,
It
A
came on
higher up
Tuesday.
department, is that what you said?
Oh,
I mean, it's not from the
yesterday.
mechanical engineering department, someone from the university did it.
Oh.
Because we sent our emails
Forget.
end of, like, in the middle of last week, actually, so, but that came from our VSW advising.
Well, it was really late. I would expect you guys to send, like, for mechanical especially, like, I'd expect you guys to send it like months in advance, which you.
Yeah.
Which usually
usually it's an event,
Which you
not
guys
the
did.
week of.
Not the
Yeah,
week.
so this,
yeah.
this is strange, and so I'm sure, you know, it's on people's radars, but I'll contact some people today. When I get to the bottom of it, but yeah, you guys shouldn't.
Is your
You guys already
CWID,
applied
do you have a
everything as
hold
applied.
on your registration account?
Yeah, I do.
Yeah.
Okay, so
Okay.
I'll CC the three of them
Okay,
and I'll I'll do it right now.
okay, yeah, I'll get to the bottom of it, and so I don't think you guys definitely shouldn't have holds.
Because we should be getting, I mean, I don't know, how does graduation work as far as the registering for classes? Is it like, how early is early?
So you guys, I think it's about a week early, just to make sure that you guys get the courses you need to graduate.
Okay.
I think for you guys, it's not that big an issue, because it's, you know, senior design, which you're gonna get into anyway,
Mhm.
and then, you know, 476B, you know.
I think, and all of us here on legacy
And then-
teams.
and
So,
then-
so,
yeah, exactly.
so it's all waitlisted
Is
anyway.
it too late for me to join Formula with you guys?
You specifically, absolutely.
No. Actually, you can, just you belong in the machine shop. That's it.
Oh, so it's the same thing with this
One of
one.
the,
I love machine
So
shop. It's fun.
when's your spring classes registration date?
I mean,
I don't have one yet.
I don't have one either.
Oh, I have one, but it's not.
Oh, I don't have one.
I'll
yet.
just have to double check like later
So
today.
another advising
yeah, I
question.
don't have one.
I don't have one.
Got like 80 tabs.
Are you still there, Charles?
There it is. There it is.
Yeah, I'm surprised his laptop's still.
Okay, you're still there.
managed.
So
Yeah, I have
some
like
jobs
two
will
tabs on this-
ask,
this one.
will ask what's the difference between them. They'll ask you to post both. But most jobs will just ask you just to put one. And so,
Oh, good,
um,
good.
you know,
I didn't check that.
if you're asking about your resume, you know, I would just put just whichever one's higher, honestly, you say that, you know,
This
my
one,
GPA
oh,
counts at
that's-
Fullerton was this.
that's a whole-
But some jobs may ask you for a transcript or overall or something like that.
It's probably important.
No, this wasn't yours. Ask for the-
Yeah, so I would just put, honestly, I just put whichever one's higher.
I literally just pronounced that you also know. I didn't.
Oh, I just found that too today.
I just got like
No,
tons of
like-
emails.
All right, any final questions on Zoom before I close it up?
I've been
I mean,
now right now.
No, I'm kidding you. I'm not kidding you. Right now too.
Yeah, we're all right now.
I literally like.
Okay, all right, so I'll see you guys Thursday.